Hey everyone, this is Brandon Monnier, and this is day 2 of the ILCI workshop JupyterHub Interop seminar slash teaching component that we did at the ILCI annual meeting in Senegal. So this is the second video in a two-part video series. For the first video, we went over day 1. This is day 2. So if you haven't watched day 1, I recommend you watch that because some of the things that I'm going to be talking about are continuations from that prior video. So the learning objectives for this video set is we're going to continue going through some of the different analyses that you can do with RTassel because we left off on day 1. Going through just like half of what we can do with RTassel. And then the second component of the meeting was kind of like looking into the future and where we're kind of going in terms of the ILCI hub and the Breeder hub in general, in terms of getting data from various types of data management systems. And we'll talk about that in the middle portion of this video. And then we'll end this video series with some examples of how you can do genomic prediction with RTassel, and then also the mixed model solver summer. So this first component right here, these are the libraries that we're using for this notebook. And another reminder that this, along with the notebook from day 1, are found on the ILCI JupyterHub server. They are found, as we go here, they're found under the shared directory, under Commons, and if you go to Notebooks, they'll be in this Interoperability Workshop RTassel 2022 subdirectory, where you can find not only day 1 but also day 2 as well, along with some additional material that we generated during those talks. So here are the packages that we're using today. So these are the packages that we used from yesterday or day 1. The new packages that we're going to be using today are Genomic Ranges, QBMS, and Summer. And we'll talk about those when we get to those components in the notebook. We're also going to be regenerating this little helper function from yesterday, which is to help control the dimensions of the plots that we create within our notebooks. And that's already been created and ran within this notebook. And then what I'm going to do is I'm going to read in the example data that we were using yesterday. So I'm just going to kind of go through this really quick. We're just reading this into an RTassel data set, and then we're creating combined data set with both the phenotype and genotype information from yesterday. So we have about 265 samples and a little bit over 3,000 markers, which makes a little bit under 820,000 taxa by position, or sample ID by position marker values. And this is just recalling that. So this first section that we're doing is, again, we're going through some different analyses. In certain cases, you may not want to work with like the entire data set. Maybe you want to work with a specific subset of data. And so RTassel provides a lot of different ways that we can filter our data down either by positions or by taxa. Or what I mean is sample IDs. So this first thing that we're going to go through is so we can filter or reduce the dimensionality of our data, or not dimensionality, but like reduce the number of observations within our data by using these filter functions in the filter family of RTassel. So this first thing that we're looking at is we're filtering by variant sites. Remember, we have sample IDs here, and then we have our markers here. We are filtering down this dimension of the matrix. So we're removing particular columns in this case. And so we can pass that in this filter genotype table sites function. And so this, if I run this and I do a little tab completion, there are a lot of different parameters that you can utilize to help with your whatever type of filtration that you are wanting to do. And again, if you need information, we have on the website at mazegenetics.github.io/rtassel, we have several different vignettes that go into this a lot further in depth and detail. There is a whole document talking about how we filter sites by all of the different components. So I'm not going to go through every single different possibility. If you want to go through every single possibility, please visit this website and take a look at the filtering genotype tables article on that. What I will do, however, is I'll go through some of the more commonly used filtration schemes. So one of the things that geneticists like to filter by is minor allele frequency. And so that is one of the parameters that we can use. And so in this example, what we're doing is we're filtering by site minor allele frequency of 0.05, which is kind of like the general cutoff for this filtration scheme. So if you take a look here, we've got 3,093 positions, and if we filter that down using this minor allele frequency, we drop down to 2,536. By doing so, we're removing, particular positions that don't match this particular threshold. And so we are reducing the number of columns in this case. We can also, in certain cases, we may not be interested in the entire genome of markers. Maybe you're interested in a chromosome, or you're interested in a section of a chromosome. What you can do is you can make things like genomic ranges. And this is where this genomic ranges library comes into play, which is kind of a standardized way of specifying links or ranges, so to speak, within a genome, i.e. where are they located, so what chromosome are they found, what's the start site, what's the stop site, different things like that. So we're just making a data frame, we're coercing that into this granges object, and then what we can do is we can pass that through one of the parameters called this positions to keep. So let's say we just want to keep all of the markers that are found within this start to this end site within our marker data set. We can filter that by passing this genomic ranges object, and we get something like that. So we get, in this case, 7 positions, and if we take a look at the position list, so we're just pulling out all of those different positions, we notice that we get, all of the markers that are found within this specific range. So 100,000 to 3 million. So here to here. And then I made a little joke because we're by samples or taxa, because we don't like the word taxa anymore, or genotype. So instead of filtering by columns, we can filter by rows in this case, so the sample IDs. And so this would be like, let's say you're interested in specific samples and not like the full data set. Like you just want to pull out all the marker information for a handful of samples. So what you can do is you can, select on, you can do like a grep search or something, or you can pass literal sample IDs as a vector. You can add that to an object, and then you can pass that through this other filter function within rtassel, which is genotype table taxa. So this one was sites. So again, we're filtering on the columns. This is taxa. We're filtering by each one of those samples or rows in the matrix. So in this case, we're just passing these 4 different taxa IDs. And so if we filter that, we got an error because I did not run that. So let me run that real quick. And we get, instead of 265 samples, we get 4 samples in this case. And so we can then prove that by pulling out the taxa list from this object, and we return these values. Like another thing too is, let's say you have something that isn't found within your taxa set, like, you know, not available. Pretty sure this isn't going to be a taxa. If we do that, we still get 4 taxa or samples that are returned, and what it does is it will try to find as many valid sample IDs that are found within your collection, and not things that are, it won't like throw an error or an exception if like it can't find every single one. Like if it can't find it, it just won't return that. So I'll just keep that for documentation purposes. Another thing you can do, and again, this is a very brief overview of what you can do in terms of filtration. Again, I highly recommend you take a look at this article, and I'll probably put a link to this at the beginning of the notebook just for additional reference. But there is a lot of different ways that you can filter a genotype table, specifically by, you know, marker positions. And, you know, again, we've gone through, you know, all of the trouble of trying to come up with every single different type of scenario. We're also, you know, in these pictures, we also work out the math of like the logic behind how these things filter, and, you know, using all of these different frequency type positions, and then, you know, piping these things together. It's a very extensive documentation set, and I highly recommend, you know, if you are interested in this, take a look at it. And, you know, let me know if you have any additional questions about that. Another thing that we can also do is we can generate, you know, we can generate matrices about how well things are related to one another within our data set. And so this is where the idea of kinship matrices comes into play. This is a very simple method in our tassel. It's aptly called kinship matrix, and what this is going to do is it's going to generate a metric of, or a matrix of kinship metrics. So either like identity by descent or several different other algorithms that you may want to choose, but the endpoint being is that you generate, you know, an R matrix, or in this case an R tassel matrix that you can then feed into like a mixed linear model to, you know, have a kinship component to define, like, you know, for variability, or you can then use this, as we'll talk later about, generating results for genotypic prediction or selection. And so to do that, you just take the data set from tassel and you pass it to the kinship matrix object. And you, in this case, we're just passing it into this kinship res object. And we're just going to call that to the console to take a look at what that actually generates. So by default, this isn't going to generate an R matrix, but it's going to present a tassel distance matrix object. And this is just kind of like an abstract representation of that pairwise matrix. So we're comparing each one of the samples within our data set to one another to generate a metric. So the higher the value, in this case, the more related they are. So if you do like self by self comparison, the values are going to be much, much higher. And again, these aren't like perfect scores of 0 to 1, because this is based off of the different algorithms that we can implement. So, and again, if you want more information, we just go to the website, search for kinship. And so we have centered IBS, normalized IBS, dominant centered IBS, and dominance normalized IBS. And these are all coming from this endomendogenic paper from 2012 if you want additional information about that. So by default, it does a centered IBS method. Hence why you get these particular values on the diagonal. We can then take this object and we can coerce it to an actual R matrix using the as.rmatrix method. And so this will now be converted to an R matrix. So we can take a look at those same values, but now it is a base R matrix instead of this abstract matrix representation. So then we can then pass that into, like, we can visualize that if we wanted to. We can then pass that into summer, which we'll talk about later on in this presentation. And several other things as well, in case you just don't want to use RTassel in this case. We have that ability to pipe these objects out and pass it to other pieces of software. And so that's kind of like the end of all the different RTassel analyses that we can do. Keep in mind there's a lot more different things that you can do in RTassel, but these are the things that are probably the most relevant to the crowd in Senegal, or just plant breeders in general, what they want to use and how they want to maybe integrate this into their future pipelines. The next couple of sections that we talked about was moving forward with the ILCI hub and moving forward with the breeder hub in general. And one of these things is, how exactly do we want to pull in data in the future? So at the beginning of this talk and the first video talking about day one is that a lot of the things that we are commonly know about are these things like flat files, these external files that we can call, from a directory that stores somewhere on the JupyterHub or on your local computer, things like that. These would be things like text files, floating VCF files, floating spreadsheets for trait data and all this stuff. One of the things that we're trying to move forward with is, what if you could just get rid of flat files altogether and instead call a data provider to return that data into a notebook that not only like you wouldn't have to worry about handling all these different files, but depending on what machine you're on, if you're on like the ILCI hub or if you're on your own personal computer, you could talk to these particular databases and return your information as such. That way you wouldn't have to always handle juggling different types of files around amongst different groups and things like that. And so we talked a little bit about this demo, about how we can get data from two different data management systems. One is the BMS, or the breeding management system, and the other one is this service through GigWa. And so you can think of BMS as returning phenotype data in RTassel, and GigWa, which is returning genotype data through RTassel and other programs as well. And so what I did is we had this little demo section, and this is still very much a work in progress, but at least at the Senegal workshop, we demoed this current state of this, utilizing this package that is called QBMS, which is a series of functions that you can call to query different databases for genotype and phenotype information using configured endpoints and such. But one of the things that we wanted to make better to help with privacy and security concerns was, how do you properly authenticate this QBMS package? And this is something that we're still working on. And this is kind of like a little demo that we showed, which is this authentication demo. So if I run these first three components, and this is in a notebook that unfortunately is not going to be shared with the public, because again, this is very much a prototype, and what we're going to actually be showcasing is going to be a major improvement from this. And this is actually not going to be a notebook, but it's going to be something like an extension that you would perhaps call within the ILCI JupyterHub or the Jupyter Lab component. So I'm just going to run these things real quick. And what this is doing is, this is calling some JavaScript, and it's basically providing a little graphical user interface that you can call within a notebook or through an extension that allows you to properly authenticate data that you may have hosted on a particular provider. So in this case, I'm going to show some genotype data, or I'm sorry, phenotype data through this BMS, which is this breeding management system. So what I'm going to do here is I'm going to go down to this phenotype data provider, and then you notice that we have these different providers that are populated once you run this little function. In this case, we're picking the breeding management system, so BMS for short. And then what you do is you go up to here to the selected providers and click the Pheno BMS button, and then you'll have this BMS login system. And what I'm going to do is I'm going to put in my credentials for the BMS, one of our BMS test examples, and I'm going to submit that. And then what's going to happen is you're going to generate an authentication token that is temporary in this case. So I'm just going to copy that, and it's going to copy it to the clipboard. And then what I can do is I can go down here, and I'm just going to delete this, and then I can paste what has been copied in this token into a cell, and then I can call this QBMS library, set up the URL that we're pointed to where this data is living, and then I can set up some token information for authorization. That way you're not exposing your own password out to the public or with collaborators or anything like that for security purposes. And then what I'm doing right here is I'm just calling this list crops component, which is, we're setting up this BMS service with our credentials, and then we're listing some information from this endpoint, so from this URL. In this case, we have by default maize, millet, rice, and sorghum. And so what I'm going to do is I'm going to go through this. These are all QBMS functions, so I can set this crop. I can list the programs. So in this case, I have this ILCI evaluations program. I can set the program, and then within that program, I can list additional trials. So I'm going to choose this Adunia trial 1, and then from that trial, I'm going to list some of the studies that are found. So you notice that there's like an hierarchical component to those. I'm going to pick one of those studies using this set study method. So as you can see, there's kind of like this pattern where we list and set things. We list programs, we set the program. We list trials, we set the trial. We list studies, we set the study. So I'm going to set that study, and then I'm going to get the actual study data, and I'm going to get the info, and I'll take a look at that pheno info, and you notice we return a data frame, and I can actually take a look at that if I remember what it's called. Oh, and yeah, this is also very much a prototype because this isn't technically R, this is Python. So we get this data frame which has all of our like metadata that we set, but then we can also take a look at the actual observations, the traits from that. We can call that, and again, it's not going to look that pretty because this is a Python notebook and it isn't really structured for R objects. And I'll just, instead of str, I'll just do head. And so this is just showing a data frame which has the year, the additional metadata information from that study info column, and then we have different observational traits, which in this case we have some traits for yield, kilograms per hectare, and we get some values. And so just like we showed yesterday with RTassel, you could then further process this and then pass this into like an RTassel data set. Or if you just want the data frame, you can just pull that out and do whatever analyses that you want to do there. So keep in mind, again, this is very much a prototype. We also have the ability of setting up not only phenotype data, but also genotype data. So we have default setups right now for Gobi and Gigwa. And then just like you would for the PhenoBMS, you could then set your credentials as such in this data sources selector method that again is going to not be found necessarily in this notebook that you'd share, but more or less like an extension that you could like call up and then, you know, put in your credentials and then make some template code and then work from there. And again, all of this is, the reason why we do this is for security purposes. We can also, you know, pull in data from GigWah using the same package, QBMS package. So we have the set QBMS config, which we were kind of doing in this demo here. But in this case, we are specifying this test GigWah server. And for this, this is all exposed to the public, so we don't have to really worry about authentication. That's why we have this no authentication set to true in the set QBMS config. So this is all exposed public data. And just like, you know, BMS, we have different methods for listing and setting different pieces of data based off of what database, you know, what projects, things like that. And so we can just list some databases here from this example data set. So we have all these different data types, and so we're just going to set, in this case, the database ID to sorghum JGI, which is an example data set of various sorghum varieties and their marker information. So I'll just set that to that particular database using a character, and then once that database is set, we can then list projects. There's one project from that database, so we'll set it to this Nelson et al. 2011. And then from that project, we have different runs, and we can again set that. And then this is where we can actually start to get the actual marker data. And so what I'm showing right here, this is a QBMS function. So this is this GigWah get variant, so we're getting the marker variant matrix. And the really cool thing about this is we have different arguments that we can pass after we set the database information and the projects and the run. We can then, you know, filter our data using GigWah, so we don't even have to do that, you know, once it gets passed into our tassel, which is this new component that we introduced in the read family. So basically you could do your filtration on the DB end and then pull down less information that way. So that way you're not like pulling down, you know, a huge marker set. You're pulling down already pre-filtered markers and, you know, particular taxa on the DB end, and then when you pass that into the actual notebook, you already have a filtered data set, which is pretty nice. So yeah, so what we're doing is we're taking this object and then we're just coercing that into a genotype table object in our tassel using this new read genotype table from GigWah method, because all of this GigWah data is structured in a specific way that we can then use these patterns to then parse and process into a tassel, and more importantly, an R tassel data object. And again, we're using that Magritter pipe method that we introduced in the last video and on day one. So I'm just going to run that. And this, depending on the connection, depending on how quick everything is, your internet, this will depend on the actual download speed. So right now we're doing some, you know, minor allele frequency filtration. Then we're also filtering on the matrix itself. So like, what's the proportion of missing values, you know, in that marker data set? And we can also filter on samples, or in our tassel speak, it's taxa. Okay, so it's been completed. So we get the nice thing about it too is you get this nice little progress bar to show you, you know, how much data has been downloaded from the database into the notebook. And now we can call that GigWah marker data, and you should see something that's very familiar. In this case, you have the tassel genotype phenotype data set, you have the taxa, you have the positions, and then you have the taxa by positions. And so if we do something like a, you know, we call this, we can go taxa list, we can call those individuals that we called from the GigWa database and pulled into here. So that is the middle part that we talked about. And again, this is like pretty much a demo for not only the breeding management system, but for GigWa, and then some of the things that we're working on in terms of authentication and making sure everything is secure for possible users for the ILCI hub and like the breeder hub in general. All right, and so for the last section for day 2, we talked about one approach or just some examples of how you can do genomic prediction within the ILCI hub. So again, one of the things that we're doing in terms of genomic prediction is, given a set of markers, can we predict the phenotype of an individual given a training set? So basically, given the profile of markers for each one of these taxa or samples, can you, like when you introduce new individuals into that population, given their like genetic makeup, how closely related is that going to be? How well can you predict the actual, trait of interest in this case? So what we're doing right here is and this is more of like a review of the data that we used yesterday, which is this. We have the sample ID. So we're taking that genotype phenotype data. We are using the rtassel get phenotype data frame, so we're extracting the data frame object, the phenotype data frame object from that genotype phenotype data set. Then we're doing some just dplyr basics. We're selecting specific columns, and to avoid confusion, we're just recalling that we're renaming that taxa column into an ID column. Okay, so in this case, we're going to be predicting on ear height, and we have a trial that's been planted in 2 locations, so A and B. And so this is what the data frame looks like after that processing. We got 3 columns. We've got all of our different sample IDs. So we got our ID, we got our location, we have our ear height, which is your continuous measurement. So the first thing that we're going to do is we are going to, from this initial data set, you notice that we have all of this like raw data, and we have multiple locations, and depending on your experimental setup, what you need to do first is to, based off of that experimental design, you need to essentially generate, for lack of better terms, kind of like a very fancy weighted mean or weighted average, given all of these different locations. And so one of the things that you can do is you can generate best linear unbiased predictors. And this is kind of different from a best linear unbiased estimator, is because how we are treating how are we treating fixed and random effects. So in the case of generating BLUPs, what you'd do is you'd have something like this. You'd have a data frame, you'd have a data set with whatever your experimental design is, and you'd feed it into a mixed linear model equation solver. In this case, this is from Summer, now this MMER, the Summer package. So library Summer. So we're using, from this package, we're using this MMER, which is the mixed model equation solver for random effects. And as you can see, similar to how the association model fitter in rtassel and how the linear model general equation is in base R, we have different formula sets. So in this case, we have a fixed component of the formula and a random component of the formula. So in this case, we're trying to generate BLUPs based off of this ear height. So this is what we want here. So this would be our Y, and then the other fixed component in this case is going to be the location. And then what we're doing is we're taking ID, So we're getting the random effect for each one of these IDs, and we're just passing that in as this tilde ID. And then, what data are we specifying? We're specifying the phenotype data frame set, and we're just going to say false for verbose. Like this verbose function is, when it's calculating, it's going to generate some additional information when it's calculating. So you can set that to true, you can set that to false. It's for the scope of this video and this training session, we set that to false because, a lot of the stuff that's being generated is probably significant, but for what we wanted to get out, we just set that to false. So it's just going to run. It's going to run the fit. And then from that fit, we can take a look at what we get. So if we call that, this actually does work. Okay, that's weird. But as you can see, if we just use structure to fit one. Yeah, so we get, it's probably just overloading the console in terms of like the actual output that's being generated from this fit one. So like a linear model object, you're gonna like pass this into another object, which is like your fit object. And this is gonna be essentially a list, right? And with Summer, a lot of the things, like if you use Summer a lot, and you have a good idea of how mixed model equations work, some of these values can make sense, but in my opinion, a lot of these things are kind of nebulous and are kind of archaic in terms of how a person that doesn't maybe have a lot of experience about like what exactly do you need to pull out of this in terms of like your actual BLEP value, because it's not very straightforward. So in this case, what we're doing is we're trying to pull out this, right? We're trying to pull out the random effects generated by this ID, right, for this ear height. And so when we call that, so this whole component right here is basically taking the BLEPs that are calculated from this solver and trying to reformat them into a more user-friendly way. Because unfortunately, like packages like this and things like LM and things like ANOVA don't necessarily generate data frames or structures that we can use for other analyses, and so you have to do a lot of what we call data munging and data parsing and manipulation of the data to turn it into a more usable, more friendly object that we can use downstream. So let's kind of go through this line by line. So the first thing that we're going to do is from this what we want to pull out, which is we want to pull out a predictor for each one of these IDs in the category for this ear height. And so that's found under this U component. So if we just do that, so from that fit one, just like a list or a data frame, we call that U, and we get this, all of this information, right? And this is not a data frame. This is like, this is a very complicated vector that we have to process. And so you notice that when we call that, there's another component that we call from this ID, or from this U component, which is the ID. And again, that's each one of those different samples. So if we call that, we get something that looks maybe a little bit better. But the next thing we want to do is, can we just coerce that as a data frame? So we go as data frame. And okay, now that's starting to look a little bit better, right? But the unfortunate thing, and for the sake of purpose, for clarity, to make things more concise, I'm just going to look at the first 6 rows. So we're taking that ID column, we're converting it into a data frame. That gives us a 1-column data frame structure with ear height as the column. So this would be the best linear unbiased predictor. And then we look at the head, and then we're just taking the first 6 rows. So it's starting to look a little bit more simpler, but now you probably notice a couple of additional problems with this data set. We have row names. For data frames, modern R just tries to avoid row names altogether. So we want to convert those to another column in the data frame instead of just having this actual row name component. So that's one thing that we have to do. Another thing that we need to do is, if you notice, we have this ID component that's been pasted to each one of our individual samples that we'll need to remove. And so this is where all of these different steps comes into play. And so just like, generating a ggplot, you have, these dplyr and tidyr kind of workflows that allow you to, use this magrittr pipe and then pass all of these different functions and components to help, munge and manipulate your data as you keep, going through your analytical pipelines. So the first thing that we're going to do is we're going to convert that to a data frame. And then what we're going to do is, in the case of if there were like multiple columns, let's so to speak, you could select that. But select also has another powerful function in dplyr, which allows us to rename columns. So we're going to select that ear height, but we're going to just call it trait blup for now. So we're going to change that for the sake of this experiment, or for this workflow. We're just going to change that ear height name to this trait blup name. And so the next thing that we're going to do, so if we now run that, oops, I should get the additional magrittr pipe there to get the first 6 rows. So now we've changed the column name. Now what we need to do is we need to change the row names to its own individual column. And luckily this is such a common problem that the package Tibble, which is found also in the tidyverse, has this really great powerful method I think more people should know about, which is this row names to column method, which, as the name implies, just turns the row names into a new column. And you can also specify what you want to call that column within this function. And this is where this var parameter comes into place. So we want to just call that new column ID. And so now, okay, it's starting to look a lot better. So we have, instead of one column, we have 2 columns, no row names anymore because we don't like row names. But now what we got to do is we got to get rid of this ID component in each one of these rows. So this is where the last function comes into play, which is from the dplyr function, or dplyr package, which is mutate. And mutate, if we look at the base definition of that, just simply means to change. So we're going to change a column. We're going to either change the data frame by adding new columns. We're going to change pre-existing columns by maybe adding a number, or modifying it. So what are we going to change in this case? We're going to change this ID column. And what do we want to do with it? So what we want to do is we want to strip off this ID component on each one of these observations. So what we're going to do is we're going to use another package. And again, all of these packages are found in the tidyverse. So these are very well published, very well used, very well maintained libraries that are very powerful and very useful for a lot of day-to-day R analytics. And so stringer is a way of manipulating text in R. It comes with a nice family of different functions and capabilities. And so one of the functions that we're going to use is this str replace. And so what are we going to replace? We're going to take that ID column. We're going to identify specific text patterns in that ID column. In this case, we want to identify this pattern, this ID, right? So we're just going to put that in here. So that's going to identify in each one of these rows this ID pattern. And then, so we've identified that, okay, if you identify that in each one of these rows, how do you want to process it? And so we just want that to be essentially nothing, or a 0 width character. So we just do this kind of blank double quote parameter here. So we have the string, in this case ID, which is a vector of strings. We want to find the pattern, and then we want to replace it with this. Now if we run that, we notice that if I, again, just kind of switch between that, we go from this ID to this new ID with no ID prefix. And so that's essentially what we've done here. We've just gone through that row by row. So I'll just do this, and then I'll pass it here. So this is the same thing. We're just adding it to this new object, which is called my blups. So we take the head of that. So these are the blups. So for each one of these, this is the best linear unbiased predictor according, or using location as a fixed effect, and then each one of the IDs is a random effect. The next thing that we want to do is we need to do the actual genomic prediction component. And on top of that too, we want to measure. We don't just want to, like, train a model and just kind of like trust that the model works, right? We want to like validate or evaluate the power of the model, or how accurate that model is. So the first thing that we're going to do is, before we even think about genomic prediction, is we're going to do some QC, some sanity checks, so to speak. And one of the things that we want to do is, so prior to this project, or this component, we generated this kinship component using Tassel. One thing that we want to check is if the kinship and blup IDs match and are in order, right? And so we can use this identical function. And so what that does is, if, like, let's say I have two vectors, x is going to be A, that's going to be B, that's going to be C, and then I have Y, that's going to be A, that's going to be B, and that's going to be C. That's going to be true. But now, if I change this to C, that's going to be false. So I'll change that to B, but now, like, what happens if, like, that's a B, and that's an A? Oops. That's also going to be false. Like, they're both the same content, but they're out of order. So it's kind of like, all these different logic checks wrapped together into this one function. And it's pretty nice if you're, one, checking for similarity to make sure like all the contents match and they're also in the same order. You can just use this identical thing, and it's going to return a true or false. It's going to return a Boolean if we want to be specific. So we run that, and we have this, we have true. So that just indicates that, everything in the ID column in this new blup thing that we've generated is the same as the column names, and we can also check row names if we wanted to. So that are met, because it's a pairwise matrix. So that's true. So that's good. We don't have to make sure everything is in fashion and in order that way, so we can continue. If not, make sure all of that lines up. It's always good to do internal checks and tests in these analytical pipelines. So the next step right here is, going back to, so we're going to train a model, right? And we want to test how good the model actually is. And so we want to, we want to train it in a specific set, and then we want to, evaluate it. We want to test how accurate this model is. So instead of just running it on all of our data and training it and just thinking, oh, it's perfect, just throw this into our applications. No, you have to always verify. And so one of the things that we do is, when we're, making predictions and, generating actual models that we can then feed into a prediction pipeline, is this whole concept of training and testing data splits. So basically what you do is, in our case, we have all of this data, right? And we have, we have an ID, and then we have a trait, a phenotypic trait, or in this case, a BLUP value that we know because we have actual phenotypic information about that. And then we also have marker data to support that. And so what we would do is we would take this data and then we're going to split it up into two components. One step or one part of the data is going to be the training data, and then the other part is going to be the testing data. So we're going to essentially train in the training data. We're going to create our predictive model here, and then we're going to feed in data that the training component hasn't seen yet. This is completely fresh, completely new. And then we're going to compare and contrast the accuracies. How well, is the predicted score versus the actual score? And so we'll go through that, step by step here. So the first thing that we need to do is we need to set up some testing data. So this first step right here is one thing we want to do is, for reproducibility, and now that we're dealing with randomization here, we want to set seeds. So what that's going to essentially do is, if I have this seed, or actually if I just do, if I just run sample and I go 1 through 10, and I want 3 values from that, right? Every time I run that, it's going to generate a new collection of samples. What I can then do is I can set what are called seeds, and that's basically going to lock down the randomization to always generate a particular set of numbers. So if I keep running this, it's going to be 310, 2, 310, 2, 310, 2. Every time I evaluate that cell, it's going to be 310 and 2. So the same thing applies here. So okay, so that's, sampling is just going to take a random collection of values from a vector. In this case, we're going to take random observations here, and we're going to get a proportion of those samples. So depending on where you read this, and this isn't going to be like, this isn't going to turn into like a machine learning tutorial session, but like, depending on, where you, get your information, or you learn this stuff, the general consensus is like, you want to have a good majority of your data to be in the actual training component, and then a portion of that being in the testing data. And so generally it's like 80% of your data gets fed into this training component, and then the other 20% is left out for testing and evaluation. So that's exactly what we're going to do here. So what we're going to do is we're going to just pick samples that we're going to mask the value of. So we're going to take some of these BLUP values and we're just going to mask it, and I'm using finger quotes here, and we're going to set those to NAs. Like, that's just missing data. Okay. So I'm going to run that. So we're sampling just those, and we're sampling approximately 20% of that. And so if I call that, or actually I don't need to do this because I already called it in this cell. If I call that and I run it again, you notice that I still get the same samples every time. But if I, would do that and then run that again, you get different collections. So in the case of reproducibility, if a collaborator or a reviewer for a publication or whatever would want to rerun all of these steps, you want to make sure that they can get the same results as you did when you did your analyses. And so that's where setting seed comes into play. So set seed, useful for randomization in data sets, or in collections collections of data. I'm just going to save this real quick. Okay, so we have our samples that we're going to mask, right? So these are IDs to NA. So how are we going to actually do that? And so this is where, again, our good buddy mutate from dplyr comes into play. So we're going to take that blups data frame. We're going to pipe it into this mutate component. And what are we going to mutate? We're going to mutate this trait blup column, right? So we're going to change it ever so slightly. So what are we going to do? We're going to use this if-else statement. So in R, they got this really cool method called if-else that has 3 different parameters. It's got a test component, and then a yes, and then a no. So like the test, so this would be like a logical component. So like any other like if-else statement, this would be something that returns a Boolean or a true or false statement. If one, like in this example here, we'll do like, and I'm just, you know, improvising this as we go. If 1 is less than 2, right? As you know, clearly we know this is not true. If it is, in whatever reality we may exist where 1 is less than 2, I'm sorry, I meant 1 is greater than 2. If 1 is greater than 2, if in any reality where 1 is actually greater than 2, let's say this is weird. If it's not, 1 is less than 2. Right, so if we evaluate that, 1 is definitely not greater than 2. Whoops. 1 is definitely not greater than 2, so it's never going to trigger this yes statement. So that's a positive result. If it's not, it's going to trigger this. Okay. This is kind of a silly example because this is something that, like, you know, is always going to be one statement or the other. So like this, yeah, this wouldn't work. But like, you know, if you're passing, like, let's say a variable like n, and then n, we pass that, and then like, I don't know, what if the variable in this case is 5, right? Like it's the this is weird option. But again, this is a very simple example of how if-else works. So what is the actual test case that we're going to be using in this example? What we're going to be doing is this ID in IDs to NA. And so what that means is we have this in operator. So we have this collection. So if we have a sample, like let's call it A, like the letter A, and we want to see if it's in a collection of other letters. So I'll just do this. C, A, B, C, C. I run that, it's true. It's going to be true. What about the letter D? That's going to be false. What about the letter B? That's also going to be true. So all it's checking is, so for each one of these observations, ID, it's going to go through each one of those observations. If it's in this collection of values that we've selected to mask, that's going to be set to true, right? It's going to be true. And then if it is, so we got the positive statement, we're going to trigger this positive statement. We're going to convert that into NA. But now if it's not, so if that ID is not in this collection, it's just going to stay the same value. So we can just pass the normal trait blup value to that. And so if we run that, and depending on where these actually land, we might have to change the size of this a little bit. So let's go n equals 20. Make sure, yep. So A239 has been masked. If we go up here, is A239 in here? I could just order this, but it's such a small sample size, I think I can just find it. Is A239 in here? Ah, there it is. A239, right there. Another thing is A632. That's right there. So yes, these are in there is 3316. And actually we could just, check this logic right here. Instead of having to eyeball it, we can use actual programming to do this. Let's try 3316. Is that in there? That's false. And then is it A632? That's true. So that's essentially what it's doing. But you don't have to manually type that. It's just automatically iterating through that. And again, if you wanted to, if you're really paranoid, you could add some additional checks after that to make sure you have the right amount. So actually, I'm just going to keep this. So again, we could pass this n parameter to the head function, and that will just dictate how many rows that we print out to the notebook. All right, so we have our training set, and so this is what we're actually going to be generating our predictive models on. And so this is where MMER comes into play again. And so yeah, MMER in summer is a very powerful equation. It can do a lot of different things. And the way that you set things up may not be, again, very, intuitive for a newcomer to this. So we passed that. So just like last time, instead of evaluating on ear height, we're evaluating on that trait blob column. And then that is the only technical. So nothing else in this equation is going to be fixed. So we can specify it with this tilde1 here. There's nothing else there's no variable that's going to be fixed. But fixed can also specify the y component to the model. The real thing that we need to be interested in is this or the random component. So in addition to that, ID of course is going to be random, but we're also going to implement another, in this case, what we're specifying as GU, which is this genomic relationship matrix. I think that's what it's short for. The unfortunate thing is you can't just pass ID plus kinship res r mat. You have to do a couple of different statements in summer to get this to actually work. And one of these is you have to pass it through this VSR function, which you can pass just collections of different variables in your model. So we can pass the ID component, but the other thing is how this actually gets fed into the underlying components of the MMER solver. And it has this GU parameter. And so that GU parameter is what we use to pass our kinship matrix object. And so we use this tilde because we're not really interested in any of the y variables or the dependent variables. We're interested in everything on the right-hand side of the equation, which are going to be your random effects. So VSR, ID, GU, which is your GRM, is going to be the kinship res r mat object. And then what data are we feeding it? We're feeding it this training set. And again, we're setting this to false. So we run that. You get this little additional piece of message here, adding additional levels of GU in the model matrix of ID. So this is for the model matrix component. So just like last time, we have a new object that we have to clean up, unfortunately. So we have dplyr and tibble to the rescue in this case. So again, we're going to go through this step by step. So the thing that you want to pull out is, since we have this random effect, we passed it into this VSR component, we have to pull out this from the U, because that's going to contain all of our predicted values. In this case, we're going to pass in this UI ID. We need to extract this u:id component. That's going to contain our predicted blobs in this case. So when we call that from this gblup answer object, just like a list or a data frame, you're just going to be doing all these different calls. And so when we call that, what exactly do we get? We get something that looks like this, which is basically a named vector. It's you know, if we pass this to print, which will actually print it like it would in like an R console. It's a vector, but it's named. So each element of the vector has a name to it. And just like last time, I'm going to just continuously pass this head component through each one of these. So just like last time, we want to convert this into a data frame. And so now, hey, we get something that looks very similar, but now our column name is this annoying little dot, so we need to change that so we can use select again. So we can rename that column to prediction blump. And so what are we going to rename? We're going to rename this annoying little dot. So that's our predicted blump. Then we have row names to column. Click that. And so we have the what are we going to change in terms of our row names here. This is going to be our ID column. So that's been converted. And then what we're going to do is we're going to take our blups. So this is that original data set that has our actual values. And we're going to merge those two things together. So the prior video and on day one, we talked a lot about how join and merge statements work. So we're just merging those two data sets together by this column, which is ID. So we do that. So now we get our trait, like our actual, and then our predicted in this case. And then we're going to filter on our completely new data. So this is going to pick the handful or so of data sets that we mask the actual values to. That didn't have any prior information about. And we're now looking at the actual trait, and then we're looking at the prediction here. And so as we can see, you can look at the prediction, and then you can look at the actual value. So that would be one way to compare it. And so that's exactly what we're doing here. So I'm just going to, again, mask this out. I'm going to pass that into an object. So now we have something that looks like this. So yeah, we could, inspect each one of these different elements within the data frame. Or what we can do is we can use some, statistical measures to see how well these each one of these observations relate to one another. And so for that, we can use the core function, which is found in the stats package, which is found in base R. And we can get like an actual metric of that correlation between predicted and actual values. See, so like essentially, do the values as like they increase, do the predicted values also increase? And we can also visualize that. And so as you can see that our predicted blups, which are found here on the x-axis, and then we have our actual blups, they correlate fairly well with each other. So we get a correlation value of 0.56 or 0.57 in this case. And again, this is example data. So keep in mind with that. So that's, what we did right here is pretty much how we kind of like ended the day, because it was starting to run a little bit late. But one additional thing that you could also do is you notice that like we only selected maybe 20 or so of these samples to like evaluate. So we train in the others and we evaluate in this additional component. What you can also do is you can do something like a cross-validation scheme, where essentially you're holding out one set of values and predicting in the other, and then you hold out on a completely new set and then predict. And you do that several times to get like an actual, predicted versus actual for your whole data set. And that way you can get like a kind of a better resolution. So unfortunately, sometimes like if you do just this, you're at like the base, you're at the whim of like randomness of like what you select. And to be more comprehensive, you can do things like this k-fold cross-validation scheme. And what that will do is, and we kind of like left off here, is kind of like how you can like group things together, and for each one of these groups you would then do each one of these like training and prediction sets and generate the predicted and actual values for like the full data set that way. Okay, so that is again one example of how you can use Summer and RTASL to do some genomic prediction for your analyses. Again, this is a very simple example that we showed, but MMER is very, very powerful, and it can do a lot of different experimental design setups. It can do a lot of different things, and so always keep that in mind when you are doing this prediction and training component. Yeah, and again, always make sure you're evaluating your models when you're training them to see like the actual versus the predicted values, to make sure you're not getting completely wrong results. You're not essentially making a random number generator, so to speak, in terms of how well things predict. But yeah, that is essentially the end of this session. So just to recap, we talked about genomic prediction, and then before that we talked a little bit about where we're going in terms of data management systems with QBMS, and then we finished off with some of the introductory analyses with RTASL. And just like another reminder is that if you have any questions, the RTASL website is your kind of like go-to place, because it has a lot of different articles about getting started doing various things, and it also has a reference set for basically every single function that is found that is actually exported out of the package that you can then follow and look at examples and look at different definitions of each one of the parameters. So with that being said, I think I'm going to stop here. And again, if anyone has any questions, feel free to reach out to me through email or Slack. Again, I also have open office hours. I constantly remind people about every week. So yeah, I hope this is of use for you watching this, and best of luck for all of your analytical needs.